let's see. Yes. So before I wanted to start talking about the topic you asked me to talk about, I just wanted to give a little bit high-level introduction into the philosophy of how I think about neural networks, if that's okay. So I sort of have two sets of slides here, one a little bit more broad and one a little bit more focused on the actual paper, if that's okay. But yeah, I'm ready to start.
Sure, that's okay, Prof.
Okay, but otherwise I'm ready to go. Should I start?
Yes, you can start.
Okay, again, so this is I really don't know at all about the background that people in the audience have, so please, just anything is unclear, go ahead and ask. So I want to start talking a little bit what are neural manifolds and why I think people should study them. Okay, so, and this is first of all to set up notation. So I assume you see these slides now, okay?
Yeah.
So in the sort of, abstract view, a feed-forward neural network is really just a particular parametrized family of functions. And this slide, as I said, is mainly to set up notation. So the theta here is the network weights or biases. In general, the whatever parameters you want to learn. So these are the learnable parameters. And then for every fixed choice of parameters, typically when you think about a deep network that has many layers, then a fixed choice of parameters gives you a function in each layer. So this f1 theta is the function in the first layer, and then there's fl theta for the function in the last layer, and you compose all of them, and you get a deep network like that. So, and often, not always, but very often, the functions in the layer have a particular form. So in the most standard architectures, this is some affine linear function that is composed with a component-wise nonlinear activation function. Okay. Sort of one basic setup of neural networks. And now, what is the neural manifold? It's sort of the central definition here, comes directly now. Okay, it's just the image of this map. So it's the set of all functions that a fixed network architecture can parameterize. Okay, so sometimes people are a little bit confused about this definition because sometimes, so this map mu here on the left of the screen, it's not a single function that eats the input vector and then output something. It's this sort of parameterizes a set of all functions that you could ever hope to achieve with a fixed network architecture. Okay, and so this is typically a complicated thing to study. Like, what exactly is the set of all functions that you can get? You can always argue that it is some manifold in some function space, but it's a complicated manifold that has, it's not smooth typically. And you see this even in the baby examples. Okay. And then if you have this view in mind of neural manifolds, then training a neural network somehow means to optimize a loss function on this neural manifold. Okay, so in most training setups can be thought of like this, in particular supervised learning. So given some training data in supervised learning, this is typically labeled pairs of input and output labels. And then what you typically, when you train a network, minimize is sort of a composed function like this. So this function here, it consists of two things. The first part is what we've seen in the previous slide. It eats parameters and outputs a function. And then the loss measures how good the function represents the data. Okay. And so we're doing this composed training typically. When you run gradient descent, you're really minimizing in this vector space on the very left. But the picture I want to have in mind to study the theory of this optimization problem is I want to sort of study directly the loss on this yellow neural manifold, okay? So I'm having this mental picture in mind where the data is a point in the same ambient space where the neural manifold lives, and that sometimes makes sense and sometimes it doesn't. And then I want to essentially find the closest point on the neural manifold given the data, where closest means whatever the loss function does. Okay, I hope that's okay. And then the typical questions that me and the people in my group are interested in studying is, if you play around with the network architecture, you add layers, or you make the layers wider, or you change what the layers do from fully connected to convolutional networks, for instance. How does then the geometry of this yellow neural manifold change? That's one question we study. And then second, if that geometry changes, then how does this geometry impact this optimization problem? So, and I want to argue that sort of certain particular points, like singularities, for instance, on neural manifolds, that they impact the optimization quite a lot. But there's many features that could have an influence on optimization, like high curvature regions, etc., etc. Okay. And so these questions are, of course, essentially the holy grail. If we would understand them, we would sort of kind of understand all the mysteries of deep learning somehow, in particular. And so people typically study this in restricted settings. So some of you might know common trends is, for instance, to study neural tangent kernels, NTKs, by looking at infinitely wide networks and studying their properties. And what I want to propose is to study in general a different simplification, to not make the architecture infinitely wide, but to keep it at finite width, but instead change or restrict the activation function to be, say, a polynomial. Okay, because polynomials, by Weierstrass approximation, can approximate anything. And so the hope is that by studying polynomial neural networks, we can say things for arbitrary neural networks. And that will open also the possibility to study neural network theory via algebraic geometry. Okay. And so there's many sort of activation functions that people at least have studied in theory that literally fall into the setting. I mean, there's a big literature on linear networks where you have no activation function. Of course, practically not really relevant, but there has been a lot of theoretical study on that. ReLU networks, which are piecewise linear, are also in particular piecewise polynomial, so they fall into the setting of that they are amenable to study with algebraic geometry. And as I said, my main focus today is polynomial activation function. Again, if there's some words that I say that some of you don't know, then please just go ahead and ask. Okay, and then in addition, if not just the activation function has an algebraic flavor, but also the loss function that we want to optimize is somehow algebraic, then the whole network training has become really an algebraic optimization problem. And then we can really, in theory, study it with pure algebraic geometry tools. And there are many popular loss functions, if you ignore regularization terms, etc., are by nature algebraic. For instance, the mean squared error is of course just a quadratic function, so in particular polynomial. If you do Wasserstein distances over discrete probability distributions, then these are in fact a polyhedral distance that's piecewise linear. And the popular cross entropy laws, I'm sure you know, that one is not really algebraic because it has a logarithm. But what is nice that if you take the logarithm, the derivative of the logarithm disappears, yeah? Then derivative of log x is 1 over x. So the derivative is algebraic, And that's nice because essentially we want to study the loss landscape of neural networks. So we don't really need to understand the loss very much itself. It's enough to study the critical points. And the critical points are an algebraic thing the moment that the derivatives are algebraic. So this story is
just a question of
yes.
sort of looping in. You know, algebraic structures are abstract in the sense that you really sometimes don't get a mental or visual picture of what the concept or the structure is. And in relation to machine learning or deep learning, but also for people who are coming from non-mathematical or entirely classical mathematical backgrounds, but maybe computer science or fields in physics or chemistry and maybe biology. In order to understand like an algebraic set or a semi-algebraic set and relating this to manifold, but also relating it to neural networks, is there, I was asking that if there is a simpler way we can get that explanation, or if the concept is explainable from a novice approach, like for a novice to understand in that sense.
Yeah, I have a baby example on the next slide. I think it's a good question. So I want to sort of argue that algebra is not really abstract. I think it just has a rumor, or like it has an image that it's a very abstract field of math. And I think it has maybe become this over the last 50 years or so. But I think originally, before sort of the term algebraic geometry even was coined, it was just a natural thing. So I think of algebra as actually pretty applied. So maybe what helps in this room is, I guess everybody here knows linear algebra, and everybody here is super well trained in doing Gaussian elimination, or at least, I don't know, we have understood that we can solve linear systems of equations very fast with numerical algorithms and so on. And for me, algebraic geometry is just the natural next step. Though, go away from linear equations and study non-linear equations. And the next easy class to study is polynomials, x squared plus 3 times x minus 17. So you just allow polynomials. I want to solve those. That's for me the flavor of applied algebraic geometry. It is just, it doesn't really have that image somehow. But in many engineering fields and also chemistry, actually super many things are naturally modeled by polynomials. Yeah, so they are kind of there. So here's maybe a concrete example of this is a baby neural network, okay?
Yeah.
So this neural network has, I want to sort of think about it as 2 layers or 1 hidden layer, depends on how you want to count it, yeah? But it eats, you see it has 4 neurons on the very left. So it eats a vector of length 4. And has 3 neurons on the very right, so it's going to output a vector of length 3. And then it has this hidden neurons in the middle. And so it has these 2 layers. And say I have no activation function, really I don't, okay, no activation function. Then the first layer is now just a linear map from R4 to R2. And that's what I mean when I write this here, yeah? So the very first layer is just a linear map that eats 4 things and then outputs 2 things. And then the next layer is a linear map that eats 2 things and outputs 3. And these are both linear maps that I can write down as matrices. So I'm back in linear algebra right now. And what this network parametrization function does, it multiplies them because it composes these 2 linear maps. So for fixed weights, I get a fixed matrix in each layer. And then the total network, so to say, is given by the product of these 2 matrices. So this is so far linear algebra. So I don't know if you have a brave audience. Now, one question would be, what is exactly the neuromanifold in this baby example. So, and that was again saying, what is the image of this map mu? What is the set of functions that this network can actually express? So I'm interested in the expressivity of this network. Which functions can I get by multiplying two matrices, just like that?
Yeah, sure.
So clearly, if I multiply two matrices, I get another matrix out. And it's going to be a 3x4 matrix, as we see here. But am I going to get all matrices? Am I going to get all 3x4 matrices when I do this multiplication? And there the answer is no. In this product, you can only obtain matrices of rank at most 2. So this layer in the middle that has 2 neurons is sort of the bottleneck that restricts the functions that this network can express. And you see, so I started sort of from a linear algebra problem because I'm just multiplying matrices. But this set here, the set of all 3x4 matrices of rank at most 2, that is not a linear vector space anymore. This thing in itself is already now kind of a non-linear space. And in fact, I can describe the space with polynomial equations because alternatively, it's all 3x4 matrices whose 3x3 minors are 0. And that's what we study in algebraic geometry. Sets that are described by polynomial equations. And so this thing is true in general. So now it's like a slightly less baby example. If I would have to have a deep linear network, so it's really the same thing as above, but now I have many layers. And so I have many matrices that I'm all going to multiply. Then the space of functions that such a network parametrizes is matrices of bounded rank, where that rank is at most whatever the smallest layer width is. So, and again, this is not a linear vector space anymore. This M, this neuromanifold, it's in fact a space that is defined by polynomial equations. The equations are coming from minors of this matrix W. And that is what we call in algebraic geometry and algebraic variety. But it doesn't matter what I call it. I don't want you to be afraid of this term or something like this. I'm just saying these are manifolds that are somehow describable by polynomial equations, and that makes them nicer. So somehow, you should be less afraid of algebraic geometry than of manifolds. Because a manifold, how can I send it to you via email? If it's very complicated, it's quite difficult. But I can always send you polynomials via email. I mean, they might be big and so on, but it's sort of more describable if it comes in an algebraic flavor. So that's the philosophy that I have, at least, of polynomial equations. Okay. So now let me get the next slide is now closer about what you asked me to talk about. Okay, so in particular, we used our algebraic geometry toolbox to study a simplified version of the very popular self-attention networks. Okay, so, and what is that? So this is a very mathematical introduction into what self-attention networks do. And the parameters of a self-attention mechanism, there are actually 3 matrices. Okay, there's a matrix Q, which stands for queries, and there is a matrix K that stands for keys, and then there is a matrix V that stands for values. Okay, so, and then for fixed such weight matrices, a self-attention mechanism does the following. It also eats a matrix. So this capital X is a matrix of unknowns. Okay, so each entry in this matrix is like an independent variable. And it eats such a matrix X and then outputs this beautiful expression. Vx, X transpose, K transpose, Qx. And what I want you to observe, so that this is there's maybe say some people of course might know self-attention, and then there is also a normalization term here that I'm skipping right now for simplicity. And then sometimes people call this linear attention or lightning attention if you don't do the normalization. But in this simplified form of attention, if you stare at this, then what you see, I want you to count that the matrix X appears 3 times on the right. 1, 2, and then at the end. So this expression is a cubic polynomial. It's a matrix polynomial. It's a cubic polynomial in the entries of the matrix X. Or in fact, yeah. It's one big matrix polynomial, or if you think of it entry-wise, itself, this is a matrix, and each entry is a cubic polynomial in the entries of the matrix X. And so we're back studying a setting where we naturally have polynomials arising. They are just there. You could write it out by hand. You could take a small example where these are all very tiny numbers and just write them down. And then you get a polynomial expression. Okay, so this is a single layer of a self-attention network without normalization term. And yeah, so here, for instance, we did this exercise for very small numbers. So these are the matrix sizes, A, D, and D prime. And this T, these are all different sort of hyperparameters. Okay, and if you make them very small, if you make just, this is all just sort of 2 by 2 or 2 by 1 matrices, okay? Then here's a plot of how does all functions that look like this, how do they look? Okay, so each point on this blue guy, each point on this blue surface here represents such a cubic function for some fixed q, k, and v. Okay, that's what I'm showing here. So each point in the blue thing comes from a fixed choice of these matrices q, k, and v. And if I change the entries in q, k, and v, then my point moves to become another point on this blue guy. So this blue is sort of a plot of all the functions. It's a set of functions that this baby neural network can parameterize. And it's a beautiful space to study that has interesting properties. In particular, it is actually not really a manifold because it's not smooth. It has some singularities. Singularities means that is points where it does locally not really look like a manifold. Okay, so there's some special points. And this is this orange curve that somehow sits inside the blue surface. And then there is some funny thing. So this orange curve actually sort of leaves the blue guy and then comes back in. This is sort of what I meant here with the dash part. So that part is actually not parameterizable by the network. It's not really there, but you could logically continue the curve like this. And in that sense, yeah, it has sort of, this blue surface has sort of 2 pinch points where this orange curve leaves and enters. And they can be, I think what's happening is at these pinch points, you have some sort of implicit bias of the neural network architecture to these points. Yes, so this is an example of a semi-algebraic set, which just means that it's parameterized in the polynomial way, which I told you, it comes from cubic equations. But
Professor,
somehow boundary points.
I have a question just right there. On this representation, the figure, every point is, am I right to think about it, since it is coming from the neural manifolds, like the algebraic set, is it every point is a polynomial, or would I be right to think about it like that? Then if that is true, how is this linked within the neural network itself, or to the layers within the neural network?
Very good question. So first of all, this baby example, it has just a single layer. Okay. So this is coming from a single layer, and what that single layer does is exactly written here in this thing. So what you see is that if you fix these matrices V, if you put, this is numbers, okay, V is fixed and K is fixed and Q is fixed, then this is some function that just depends on X, okay? And each point on this blue guy is such a function. So I don't know, I could try to draw something here. So for instance, this point here could come, it could be such a function that comes from, I don't know, what was now I'm just making some numbers up now, okay? So V could be, this should be a 1 by 2 matrix. So it could be 0, 1, and all the others have to be 2 by 2 matrices now. So I don't know, I'm just making something up. Maybe Q is the identity, and K is, I don't know, this. Okay, so this could correspond to this point, while maybe this point over here is also a cubic function. This is also such a function, but it's a different function, namely a function with different parameters, where maybe V is something else. I don't know, what are your favorite numbers? Okay, so each point is such a cubic matrix function, but they differ by plugging in different concrete choices of V, Q, and K. Okay. Yes, so that's sort of how I want to think of this. And so if you train a network, so if you train a network, then what you would do, you would want to learn with gradient descent, for instance. You want to learn V, K, and Q. And typically what you do is you do some sort of initialization. You pick some random choice of V, Q. It doesn't have to be random. People have very elaborate initialization schemes. So you pick in some way, you pick an initial choice for V, for K, and for Q. And that could be, for instance, this green point over here that I was drawing. Maybe that's what you pick as initial choice. And then with gradient descent, you would somehow then move inside this blue space until it converges to some V, K, and Q that minimize the loss a little bit better. That's sort of the picture, how this is related to network training.
Okay. So I'm quite confused. I'm quite confused with that. You said that the points are functions.
Yes.
Are they functions or the zeros of the functions?
Can you see the last part again? If these functions are
like the zeros, that's what they call zeros of the functions or zeros of the polynomials. I thought each point on the polynomial is like a zero of a polynomial and not the function itself. Just wondering if it.
Yeah, no, so this is each point here is really, so that's why I tried to mark this. Okay, so if you plug in, for instance, this green choice here of V, Q, and K, then this is a function in X. This is this function here in the middle.
Okay.
And the point there is really that function for that choice of V, Q, and K. That is what this point is. Okay.
Yeah, okay.
So each point represents a function. So it's a little bit funny. And so sort of the whole blue thing is really a manifold inside a space of functions. So it's like it has a crazy ambient space, right? It's not just R3 or something. I mean, it's like this manifold sits inside the space of cubic matrix polynomials. Okay, that's where it lives. And each point on this blue manifold is a particular cubic function in X, where particular means it looks like this for some fixed choice of V, K, and Q. And now the magic of algebraic geometry is that if you have a space like this blue space that is parametrized in the polynomial way, then the whole blue thing, although it lives in a crazy space, and although each point represents functions and it's like complicated, but the whole blue thing on its own has an algebraic structure. So if I can send this blue guy to you via email, because there is other polynomials that are not on the slides that implicitly define this thing. So I could literally, you could compute them. This is a fun exercise, and I could send them to you via email. And yeah, so sort of each point on the blue guy represents a cubic function, but also all of these blue points together, they are forming a particular type of manifold, namely a manifold that is the zero sets of some polynomials. In that sense, you're right, but I have not showed these polynomials on the slides, but it is true that each point here also satisfies some polynomial equations, but these are polynomials where the unknowns are, yeah, you have to think about how you want to phrase this, because our ambient space is the set of cubic matrix polynomials. So it's these polynomials have unknowns that are coefficients. It's a little bit technical. Okay, I don't want to dive into that too much. But if you want to think of it just from the applied perspective, then it's enough to say that each point on the blue guy represents one particular function. And when you do gradient descent, you're essentially walking in this blue space from one point where you initialized to another. Okay.
Yeah, okay. Thank you.
So this is sort of my high-level overview on things that we study here in my group, which is essentially neural manifolds for various neural network architectures. But the main point that we try to do with that paper is, I mean, we also wanted to understand the space of functions, but I think it's in general quite difficult, so we only did it for single layers. But what we were interested in is an understanding, is it possible, and how is it possible, that two different choices of V, K, and Q give you the same function? If that makes sense. But I mean, it could be that this function here is actually equal to this function. Maybe I should use prime, I use tilde. And maybe there is other matrices, V tilde, K tilde, and Q tilde, such that the resulting function is the same as when I worked with V, K, and Q. And that is the question of, sometimes people call this the hidden symmetries of a network. How can you change the parameters without changing the function that comes out? And what we did in our article is for deep networks where each layer is such a lightning self-attention, we characterized what all those hidden symmetries are. And the difficult part is not to observe those symmetries, but the difficult part is to prove that you found them all. So I'm now changing to this other set of slides that you see I didn't make. They were made by Nathan Henry, who was a student who did an internship here with me last summer. Okay, but I'll just show you. So he gave a slightly less technical introduction into these attention networks. But here's sort of this function, okay, this question. Yeah, so which choices of V, Q, and K result in the same function, even for a single layer? And what you can observe is the following. Imagine you start from V, Q, and K, and then you scale each of these matrices by a number. Okay, so here these numbers are called alpha, beta, and gamma. But again, these are just some numbers: 17, 42, 3. Okay, if you do that, and you plug that into this formula, so you plug this into this formula. Now with these scalings, you get this. But since these are just scalars, you can pull them to the front. And you see that you do not change the function as long as the product is 1. So this is a not very deep observation here. But it says that that's one easy way of how to change V, Q, and K to different ones without altering the function that comes out. So there is indeed true that generally for a function, there's many parameters that get you the same. But there's another way how to obtain, how to change parameters without changing the function. And this is sort of just, I mean, it looks a little bit technical how Nathan wrote it, but it's really just an observation that in here you have this product Q transpose K. And what I want you to think of now in the middle here, you can squeeze in an invertible matrix as much as you want. So if I do this for an invertible matrix, then I added an identity and it hasn't changed anything. So if I change my Q matrix like this and my K matrix like this, then you just compute that this of course doesn't change this part of the, this product. Okay. So again, these two things that I'm writing in the scaling and multiplying Q and K by an invertible matrix and its inverse, these are two ways on how you can change the matrices V, Q, and K without altering the output, without changing this function. And then now comes first theorem that this is everything you can do. Okay, sort of generically. Okay, but ignore this word generically for a second. But essentially, there is no other way on how to start from V, Q, and K and change them without changing the function. This is everything. And that's something you have to prove. Okay. Is there a question about this this symmetry part?
For me, maybe not now.
So my question could be that if we scale or multiply and we get maybe similar functions, are those what we call the parametric spaces for that? I don't know if it's, are they the parametric spaces?
I'm not sure if I understand the question, parametric spaces.
It's some sort of equivalence between, okay, because you're talking of having a function and we could write it, you could just multiply it with some scalars and get a similar thing, yet the initial input was quite different because if you look at this V...
That's the idea, that's the idea.
Yes?
That is indeed sort of the idea. So for given your favorite function that this network can output, can I understand all the parameters that give you that function? And these parameters might look quite different or not. I mean, the scaling part maybe does not make them look very different, but if you the second part is multiplying with an invertible matrix, it's maybe looks a little bit more different. But that's the idea.
All right.
So just from where Brian has stopped, I really want to project this to the neural networks. Now, in terms of really stacking the networks or the layers of a
Mhm.
neural network together. This effect of having this sort of effect where you're scaling these parameters, I would say, and you end up with a similar function. Would this mean that sometimes within our neural networks, we have some sort of redundancy layers?
Exactly. You're going to have redundancy. There is always some sort of form of data independent over parameterization because you have many parameters that output the same function. And it doesn't matter where in your parameter space you were walking, they will give you this is exactly what's happening. You have some sort of over parameterization. So sort of if you want to count, for instance, wait, where is this slide now? If you want to understand how expressive an architecture is, then just counting how many the size of the parameter space is not the correct measure because of this type of symmetries. The question is really, what is the dimension of the neural manifold? Okay, let me ignore this.
So it's possible when researchers are overhyping the size of parameters within their networks, and when you dig deep into those networks, you might find that 30 billion parameters, maybe like 3/4 are the useful parameters. And
yeah, exactly. So we did. I mean, now I didn't have this on the slides, but we have it in the paper. So I think even for exactly. So let me. But I could. Okay, now you see things that are maybe not. I'm just wait a second. I'm going to my web page, and I'm going to the paper, and there we have this slightly more applied sentence there. So this is sort of this type of this paragraph, yeah. So we did in some sort of example, okay? So the number of parameters, the size of the parameter space could be, for instance, roughly in this order, okay? There's some parameters, d squared L here, but it's something like this, okay? But there is some over parameterization, many parameters giving you the same functions, and so the dimension of the set of functions you can truly get is just this, which is smaller. I mean, smaller by a constant, but the constant is like 3/2, which means that you have 50% more parameters than the functions that you can actually parameterize.
Okay.
Right? And so really sort of it's good to understand that counting parameters is a first good thing, and you should do it. You should definitely understand the space of parameters that you have. But it might not tell you the true answer on how many different functions you really get out. Okay, and there's sort of this very helpful, so if you're doing this in an algebraic setting, again, if you restrict yourself to polynomials, in algebraic geometry, you have a beautiful dimension theorem, which is not very difficult because it's really, from your linear algebra class, as we write it here on the slide, you know the rank nullity theorem. Yeah, so what does the rank nullity theorem say? It's if you have a linear map, right, then what does it say? It says that the rank of a matrix is the dimension of the domain, I mean the input vector space, minus the dimension of the kernel. Okay, this is very well known in linear algebra. And now if you have a non-linear map, then this is also true. And this is this gray box up there. So the dimension of the space that it parameterizes is the dimension of the parameter space minus, and now we don't have a linear matrix kernel here. Now you have to think about the dimension of your hidden symmetries. And that's how you can count the true expressivity if you understand these hidden symmetries. Yes, but sort of last thing I wanted to say is, so now so far I've only talked about attention networks for like a single layer, okay? So now, sorry, I had this like handwritten slide that I added this morning. So far we only just talked about a single layer of these lightning attentions, but of course you want to study deep networks, okay? So now I have L such layers. Each of them is such a cubic matrix polynomial. And I just compose them. I plug in one into the other, and it becomes very messy. And this is very complicated functions that you got, but they are still polynomial. So it's the same thing. I just keep composing these things, just as you compose functions. That is now a deep lightning attention network. And the same question is, what type of symmetries can you get? And you, of course, have the symmetries that we observed in a single layer. Yeah? I can do the scaling by constants. I can do that, okay. And this adding an invertible matrix between the K and the Q matrices in each layer. So that is just what I showed you on the previous slide, nothing new. Okay. But in addition, there is something else. And this is something you might have to sit down and see it on the paper. What you can do is, now if you compose many layers, then you can sort of modify the output of, say, layer I, and then you have to cancel it in the next layer. And how you can cancel it is by modifying all the matrices in the next layer by the inverse. So you have to trust me that this is how it is, or they have to actually try to plug it in. Okay, but that is some sort of symmetry that you can get by composing, that you obtain if you compose layers with each other. And the hard part is, again, that we somehow managed to prove that these type of symmetries are all of them. So also for deep attention networks that don't work with normalization, we can say that this is all symmetries you have, and that's how we can exactly understand what the dimension of the space of attention networks is by the same argument as before. So we sort of understand how much over-parametrization there is coming from the parameters. And that's all I wanted to say, I think. Sorry for the technical talk, but it was difficult to estimate what the background knowledge is of people. It's always difficult.
I have a small question, or maybe just an inquiry. Yeah, so I'm from an algebraic geometry background, but I'm wondering, okay, the manifolds you're displaying were all having singularities, and would this be interesting if there were no singularities? Just imagine a smooth surface, and would all this really be interesting?
That would indeed be very interesting, because singularities can be good or bad. And I think it's not 100% understood yet what happens, but it depends on the type of the singularity, whether this is good or bad. If you're interested, we are discussing this. Sorry, what do I want to do? I want to go here. So we wrote this sort of high-level paper, an invitation to neuroalgebraic geometry, where we are discussing this question about singularities quite a bit in particular. So singularities can, on the one hand, lead to implicit bias towards smaller architectures, which could be desirable, but it can also lead to numerical instability in your gradient descent method. And it is good to be aware, at least, of the singularities and what type of feature they cause. And we have, for instance, seen that convolutional neural networks seem to have less singularities than fully connected networks. And yeah, so it's interesting for sure, but it's not exactly understood. I think that's how good versus bad it is.
I think I should look out for that paper, because I just want to see the connection.
Yeah, no, this implicit bias thing is not so easy to see, but we explain it nicely in this article, I think. And it's a really
the one you displayed right now?
Read article. Yeah, the one that I'm still showing. Yeah, I mean, you find it on my webpage. And that it is, this one is really very high level, and it should be very readable. It is not a super technical paper. It is really more explaining the philosophy on, and yeah, sort of this catalog here, for instance, why singularities of neural manifolds, as you see in this table, have something to do with subnetworks and so on.
Okay, thank you.
Yes, so I have to run very soon because I am responsible for daycare pickup today.
Does this mean the end of the presentation?
Yeah, I think so. Yeah.
She concluded.
Thank you very much, Professor Catherine. You really have put up a good show, and bridging the gap between computer science and mathematicians. And then I know we have friends